Well, last week we pretty much got through talking about Diels-Alder reactions, and we got some practice with that. Definitely work on this in your studying. We'll have a quiz on this next week.
Next week, Wednesday?
Sure, let's say Wednesday for all of Chapter 17 stuff plus whatever else. All right, we talked a little bit about the endo rule. We talked about the reaction. Now we need to talk about the molecular orbital description of cycloadditions, and if we still have time, we'll also get into regioselectivity, but I don't know if we'll make it there or not. We spent all that time talking about molecular orbitals and how to build them in conjugated systems and so forth. Now we want to show how to use those to talk about cycloadditions. And we'll start with the Diels-Alder because that's what we've been talking about, and that one's a little bit easier. And then we'll move to electrocyclic reactions, which will require a little bit more thinking about it. So recall that we had something like this. All right, this is what the molecular orbitals for butadiene looked like. Don't worry about, well, okay, so on the left you've got butadiene. On the right you've got ethylene. Can you guys see that? It seems dark today or something. Washed out. Is the other one better? Is it? That looks okay, right? It's still a little weird, but yeah. All right, well, I'll zoom in and see if it's. At least you can see it that way. So you've got on the left here the orbitals of butadiene, which we talked about at length before, and we have the HOMO and the LUMO, the highest occupied, the lowest unoccupied. And then over on the right, you have the molecular orbitals of ethylene. Again, the HOMO and the LUMO, only two orbitals in that case, the simpler one. And we talked about last time how the Diels-Alder reaction is a reaction between a diene and an ethylene, essentially. And we can use the molecular orbital depiction to actually show how those reactions would work. Because remember that the HOMO of the nucleophile is going to put its electrons into the LUMO of the electrophile. That's how reactions work. Just we said that in general, that's how we can describe pretty much anything that happens here. Now, which of the two, we didn't really talk about this before, but which of the two do you think is the nucleophile? The diene or the dienophile, the alkene?
Diene or dienophile.
Better? Worse? Can you guys see okay with your papers? The diene is the nucleophile, simply because it has more electrons. That's generally how we think about it. The diene is what we're going to call the nucleophile here. And this is what we'll call the electrophile. So that would follow then that the HOMO of the diene puts electrons into the LUMO of the dienophile, the alkene, and that's how you get your bonds, that's how you get your Diels-Alder reactions. To show that from an orbital standpoint, what we can do is draw the HOMO and the LUMO on each of these molecules. So we're going to take the diene and kind of look at it on its side and draw the HOMO on there. And if you don't remember what the HOMO looks like, you can derive it from that chart, but it's just this. Okay? So it's this shape, 2 in phase, and then a node, and then 2 out of phase. So we're going to draw that now on this. So we've got 2 in phase, and then a node, and then 2 more in phase, like that. So that's the HOMO superimposed on the molecule. In the same way, we're going to draw the LUMO of ethylene superimposed onto the molecule. Once again, here it is. The LUMO is where the two are out of phase, the pi star orbital. So we're going to draw that on here. Okay. And so what you can see now, maybe, is that the HOMO and the LUMO actually line up in the way that makes sense for this reaction to continue. So we've got these two orbitals that actually do have the same symmetry. The HOMO of, we can say that the HOMO of the diene has the same symmetry as the LUMO of the dienophile, and therefore they can interact. So you can see open, open, closed, closed, or whatever you want to call it, empty, empty, filled, filled, however you want to describe that. You can see that they match up. And so in fact, that's sort of what a orbital picture would look like. So then you no longer have any of these pi orbitals anymore, except for these two that didn't participate, and so now you make a new HOMO and LUMO there. That's the bonding one. The other one's the anti-bonding one. Right. There's a good picture of this in the book that I'm not going to try to draw. Let's look at it. You've got the HOMO of butadiene, which we just drew, the LUMO of ethylene, which we just drew. They come together to form those new sigma bonds. And so now you have something like this. And that's your Diels-Alder product. Okay? So in the context of a Diels-Alder reaction, there's not a whole lot we learn here, except this is how we explain the stereochemistry of the Diels-Alder reaction. The fact that the LUMO and the HOMO line up like that means that they're going to come in from one side. That's how, remember last time we talked about how the stereochemistry stays the same? As you can see here, the ethylene doesn't need to twist or do anything weird to line its orbitals up. They simply line up, so it can come right in from the bottom or right in from the top. Okay. So now where it does become important is when we talk about some other cycloadditions. Or, I'm sorry, yeah, some other cycloadditions. Whoops, hitting the wrong button, sorry. You can use the molecular orbital descriptions to determine whether or not a certain cycloaddition is going to be allowed. As we would say, symmetry allowed. For instance, here's another type of cycloaddition. Ethylene plus ethylene leads to cyclobutane. You can draw arrows, you can draw mechanistic arrows that would potentially do that. And this is called a 2+2 cycloaddition. The Diels-Alder reaction is a 4+2 cycloaddition. So we can say, are 2+2 cycloadditions symmetry allowed or not? Are they likely to happen or not? And what we do is we look at the HOMO and the LUMO of the two reactants. So the HOMO of an ethylene is going to look like this. Same one we've just discussed. And the LUMO of an ethylene looks like that. And as you can see now, these two line up, but these two don't, right? Those phases no longer line up. So what that means is, in fact, you won't form cyclobutane from a cycloaddition of two ethylenes. Two alkenes don't react to form a cyclobutane under these conditions. And we can predict that just by looking at the two orbitals. The HOMO and LUMO line up, you've got a reaction. If they don't, you don't. And that's going to be generally true for a lot of other reactions too, although in other types of molecules, it's not always as easy to draw the HOMO and the LUMO. So that's why we don't always use this when we're looking at nucleophilic substitutions. But using calculations like Cygress, you actually could. You can see if its symmetry lines up. All right, now in fact, there's a way to sort of get around this. I don't want to say get around it, but a way to get this to happen. And the way to do that is to change the HOMO or the LUMO. And how do you change the HOMO and the LUMO? Any ideas? No, actually. Good idea, but what's another way? Close. What's another way of putting energy into a system besides heat?
Reacting with something.
No, not catalyst. What?
Reacting with something else.
Reacting with something else, but what if we wanted to keep the same thing? There's two ways to put energy in something. Heat and what else?
Well, another reaction. Are you saying like?
Light, yeah. So heat and light are ways to transfer energy from one thing to something else. And in fact, you can do this with light. So let's talk about what happens when we've already talked about this a little bit. But you can see here, this is from your book, that when ethylene is excited by light, or when any system is excited by light, we talked about this in lab, one electron gets promoted from here to the next one up. Remember that from Monday? Okay. In doing that, you've effectively changed your HOMO, because the highest occupied one is now the one up there. Right? So that's exactly how you can get these reactions to happen. Now let's try it with light. Remember, light is often abbreviated H nu. So with light now, we draw the new HOMO. That's caused by that promotion of the electron. And that can still react with the original LUMO of a non-excited molecule. Sometimes this is known as the HOMO star, the excited state HOMO. And now you see that, whoops, I drew it backwards, but hang on. Let's fix that. Because of course you can always flip this thing over however you need to. Now you see that you have that match. So what that means is, in order to do this reaction, the key ingredient here is light. You can do this with light because you need the excited state of one of the molecules to actually do that. All right. So what you should be able to do now, and there's some problems in the book helps you with this, there's not a whole lot of examples here. But you can predict whether or not a cycloaddition will happen by looking at the HOMO of one, the LUMO of the other, and seeing if the orbitals line up or not. Okay? If they don't, you can try promoting one of them using light, looking at the new HOMO, and trying it again. All right. So let's try this now in the context of what we call electrocyclic reactions. Electrocyclic reactions are kind of like cycloadditions, but they all happen in the same molecule. So we're talking about these types of reactions. you've formed a ring based on removing some electrons around the structure. Electrocyclic. So now, what we're going to use, we can use the orbital chemistry, the molecular orbital theory, to determine the stereochemistry of the outcome here. All right. So let's look at the two possibilities for the stereochemistry of this type of reaction. And then let's look at the molecular orbitals and see what seems more likely. We're going to use a slightly different one. If we imagine, and these things are generally reversible, but we can imagine two ways in which this thing could cyclize. It could, and we'll talk about this mechanism and how we see this and how we know it in a second. We could end up with the methyl groups on the same side, or we could end up with the methyl groups on the opposite side. And it's an enantiomer. The top one doesn't have an enantiomer because it's achiral. It's meso. Okay? And as it turns out, you can control which product you get. So the first product comes about when you heat it up, and the second product comes about when you expose it to light. So you can imagine maybe what's going on here. One's going to use the sort of the ground state HOMO, the regular HOMO, and the other one's going to use the excited state HOMO that we've just talked about. So let's look at the orbitals of this molecule. This effectively it's a hexatriene. It's really an octatriene, I guess. And try to figure out what's going on here. So we don't need to necessarily go through the whole business of it, although it might be good for you for practice. But let's just look at the HOMO and the LUMO. And we did this before, so you can go back to your notes if you don't remember where this came from. But the HOMO for a triene, a conjugated triene, looks something like this. Okay? So it's got 2 electrons. And then the LUMO, or the next one up, has 1 more node, so we can draw that one also. So 1, 2, 3 nodes there, 2 nodes here. Let's draw those in. And the important part of doing this, actually wait, that's not right. Sorry. It actually doesn't matter for this type of problem, but we might as well try to be consistent. Okay. The important part of this, if you go back to some of those orbital diagrams we've looked at, each time you go up a level, you switch the symmetry of the ends. So like this one, the ends have the same symmetry. The one above they're opposite. And this one's empty, so this becomes the HOMO, and this becomes the LUMO. Now to figure out what's going on here, we once again superimpose the HOMO or the LUMO onto the molecule and see what needs to happen for it to form its particular product. So let's look at the HOMO, for instance, on this one and try to sort of lay it out as best we can. And I'm going to show you a shortcut in a second. Actually, don't need that one. And then we should draw the substituents as well. So these are double bonds. They don't rotate. So this methyl group is over here, and this methyl group is over here. And then the hydrogens are coming into the middle. Okay. Now to do this reaction, to do the cyclization, what's going to happen is these are going to rotate so that the p orbitals can line up in phase and become a sigma bond, the same way they did in the Diels-Alder reaction. So if you imagine your p orbitals as your thumb sticking up with the two phases, how are they going to rotate so that they match up? Are they going to go the same way, or are they going to go opposite ways? Opposite, right? They have to sort of turn in so that the filled parts line up. And we imagine this one turning clockwise and this one turning counterclockwise or anti-clockwise. And then we don't really need to care about all the rest of the orbitals, so I'm just going to draw sort of a circle around. This is kind of a thing. And so we now have this one and this one kind of pointing at each other. Okay. And now they can bond. Now the important thing is, what happened to those methyl groups when we did this? Are they both going to end up, or is one going to end up and one end up down?
One up and down.
Well, let's look at it. So we've got this methyl group out that way, this methyl group out this way, and we're rotating them opposite directions. So they're both going to go up, right? In other words, let's draw some more arrows here. So this one goes up this way, and this one goes up this way if you imagine those bonds rotating, right? So that means that in this product, the methyl groups are going to both be up, and the hydrogens are down. And this is called a dis-rotatory cycloaddition because they rotate in opposite directions. If they rotated in the same direction, you'd have a con-rotatory arrangement.
Is that where we would see the transponder?
Right,
With this rotatory, they rotate in opposite directions?
right. It doesn't mean that the substituents end up on opposite sides. It has to do with the rotation, whether they rotate the same way or not. Now, as you might imagine, if we try the same thing with the LUMO, we'll get the opposite result because the symmetry is reversed. Okay? So in fact, that's true. The LUMO is a con-rotatory cycloaddition, and what that means is that depending on what the HOMO looks like, gives you which product you're going to get, which stereoisomer, which diastereomer. So you do this in heat with the ground state HOMO, you get the dis-rotatory product where they're on the same side. You do this in light, where you have now a different symmetry, excited state HOMO. It goes con-rotatory, and you get this in, you get the other one instead. So let me show you the book's pictures just because they're a little prettier than mine. you can look at these as well on your own. But here's an example of what that would look like as a disrotatory arrangement. You see the p orbitals rotating opposite ways, and then those outside things end up both down if they rotate that way. Similarly, here's what a conrotatory arrangement looks like. If they're opposite phase, they both go in the same direction, so the reds line up, and the substituents that were on the outsides end up in the opposite way. Okay? All right. Oh, so depending on the number of electrons, you're going to have different behavior. There's a nice little table in the book that talks about the thermal versus photochemical cyclizations. Thermal is, of course, the heat, and photochemical is the light. If you have 6 electrons, you'll do what we just found right here. If you have 4 electrons, you'll actually have the opposite because the phases are switched. If we go back up to our butadiene HOMO, for instance, you can see that those phases are not symmetrical, or are inverse. So for butadiene to cyclize, you'll have the opposite stereochemistry. You'll have conrotatory cyclization for the ground state and disrotatory cyclization for the excited state. You can also imagine that these can break in the same way. So you can have So there's actually another, because these are in equilibrium, you can actually break them up as well. And that gives you a little bit more control over what's going on. So I think that pretty much takes care of this stuff. I don't want to confuse you too badly on this in the minutes before our exam. So are there any questions or things you want to talk about more with this?
So be through the end of chapter 17
Yes, Wednesday. Oh, well, Monday, but quiz is Wednesday. Yeah. Okay.